In this example, we're going to add the extra dimension of having dissipated energy. Okay, so this we have a 0.25 kilogram egg drops from a platform that's 10 meters high. And we'll go through and look at the gravitational, potential, kinetic, and then dissipated energy as well. As it's released, we see that the velocity is equal to 0, so we know that kinetic energy is going to be equal to 0. We've been given the information that the dissipated energy is also equal to 0. So the only energy form that we have is the gravitational, and we know we can figure that out from mass times gravity times height. So we take our 0.25 kilograms times gravity, acceleration due to gravity, 10 kilograms, 10 newtons per kilograms times our height, 10 meters. And we find out that our energy here is 25 joules. And our energy pi is all, whoops, hold on to that, in that it is gravitational potential. We add it all up together, what we have is 25 joules. Again, how did that energy get there in the first place? We had to do work to this system. All right. How about halfway to the ground? And we know that if it's halfway down to the ground, we've lost half of our gravitational potential energy to something else. Okay. We also see in this case that we have 1 joule, I'll rewrite that, 1 joule of dissipated energy, and our total energy stays the same at 25 joules. So what do we have left over for our kinetic energy? From that we can see we have 11.5 joules. Make sure I have my units in here because we know that our total energy is equal to all of the energy that we're looking for in the system. Let's go to our pi before we look at our velocity. So we know that half of this is our energy, our potential gravitational energy. We've got a little bit of dissipated energy, and then we have some kinetic energy. The question here is, okay, how much velocity do I need for that much kinetic energy? So our kinetic energy is equal to 1/2 mass times velocity squared. Let's go ahead and figure that out. So I put in the values here. As I mentioned before, some of you seem to be more comfortable with that, so I will demonstrate it that way. Move this around. I'm going to isolate for velocity. And 1, I have to multiply each side by 2 to clear the fraction, and then divide by the mass. Okay, so I'm going to get velocity squared is going to be equal 2 times 11.5 joules divided by 0.25 kilograms. Let's take the square root of each of those sides. And I get velocity is equal to, that's equal to the square root of 92 meters squared per second squared. Take the square root of that, I find that the velocity there, okay, is 9.6 meters per second. That could be plus or minus. So we'll just worry about the positive value. Okay. Let's take a look all the way down. When h is equal to 0, a little correction here. This should be 2.5 joules. Our total energy is again going to be the same, 25 joules. Our height is 0, so now we know our gravitational potential energy is 0. So how much kinetic energy do we have? Well, again, we look at our total energy is our gravitational potential energy 0, plus the kinetic energy, that's what we're looking for, plus the dissipated energy now, 2.5 joules. I take 25 joules, subtract 2.5, and I get my kinetic energy is 22.5 joules. Let's go ahead and draw a little diagram on that. We know that our dissipated energy is getting a little larger here, and the rest of this is kinetic energy. And if we were asked for velocity here, we could use that same format that we did here. We'd find out the velocity down at the bottom, 2 times our kinetic energy divided by our mass, take the square root of that, is 13.4 meters per second. Again, you see that the velocity hasn't doubled, even though we have almost twice as much energy.